Okay, here's a video on lesson 90, which is on mutual exclusivity. So the top is just a summary of independence and the rules of intersections. So what we're doing today is we are looking at mutual exclusivity. So mutual exclusivity is like independence, but for OR probabilities. And what it means is that two categories don't overlap, or the probability of A and B, the intersection, is equal to 0. Now, it matters that events are mutually exclusive because only when they're mutually exclusive does the addition rule work for ORs. So, if I'm looking at this first scenario, the way that we fill these out, we create a Venn diagram like this one you see in green here on the bottom right. I have shape tools, so it's a little unfair, it's a little neater. But here's what we do. We always place the middle first. So there are 230 students that play soccer, 190 that play basketball, 60 students that play both sports, and a total of 500 students at the school. So if I'm looking at this Venn diagram here, let's say that this over here is soccer, this circle. This circle over here is going to be basketball. There are 60 students that play both. So that's the number you put down first. Now what we need to do is we need to subtract in order to figure out how many go here. Because if I said there are 230 students that play soccer, right now I have 230 plus 60 is 290 students. Well, that's too many. There are only 230 students that play soccer. So when you fill these in, you use subtraction. So 230 minus 60 equals 170. And now these two will add up to 230, which is the number that I wanted up here. Now, in order to figure out how many play basketball, there are 190 that play basketball, but there's already 60 down. So 190 minus 60 equals 130. So the 130 students who play basketball only. And now the last number that needs to come into play is the total number, which is 500 students. If I add these up, 170 plus 130 plus 60, I get 360 students. Well, that's not enough. There's supposed to be 500. So what's the difference? 500 minus 360 is 140 students that are unaccounted for. Well, those are just students who aren't athletes, and they go on the outside. Now we'll use those to answer a few questions. How many students play soccer only? 170. What is the probability of soccer and not basketball? That's what this means. Soccer and not basketball. So these guys play soccer and not basketball. These guys play basketball, so they don't count. They're excluded. These guys play basketball. I need it to be and, so it needs to be both criteria. Well, these guys don't play soccer. So it's going to be only them for question 5. So there are 170 out of the total, which is 500. Now, how many students don't play either sport? We answered that already. That's 140. And lastly, what is the probability of soccer or basketball? So these guys play soccer or basketball. These guys play soccer or basketball. And so do these guys. If you ask them, do you play soccer or basketball, all of them would say yes, they do play at least one. So if I add those up, I get 360 out of 500 students. So for ORs, we add up all three, inside this, and inside this. So you can practice that, of course, with question 12 down here, if you'd like to create that Venn diagram. Now I'm going to go through one that was on the homework. Question number 27. A school newspaper took a survey of 100 students. The results of the survey show that 43 students are fans of the Buffalo Bills, 27 students are fans of the New York Jets, and 48 students do not like either team. How many of the students surveyed are fans of both the Buffalo Bills and the New York Jets? So they're implying that there is a number in the middle, but that we don't know what it is. So let me create a Venn diagram real quick. Okay. So they said that the total has to add up to 100. They said that 48 students do not like either team, so I'm going to put them out here, 48. 27 are fans of the New York Jets, and 43 are fans of the Bills. So let me label these. So we'll call these guys the Bills, and this circle will be the Jets. If I put the numbers in the way that they're written, there are 43 students that like the Bills, and there are 27 students that like the Jets. 48 plus 43 plus 27 equals 118. Well, that's too many. I'm supposed to have 100. So I double counted 18 people. So let's try it this way. If I take a guess and say that that means that there's 18 that go in here, to find out the Bills, 43 minus the 18 that are already there gets me 25. Now for the Jets. The Jets have 27. 27 minus 18 is going to be 9. And now let me check again to see if I can add these up. I'm going to erase the scratch work. If you want that work, just back up. So 48 plus 25 plus 18 plus 9. I'm going to add these in pieces because I don't want to switch my calculator. So this right here is 4 and 2 is 6, round up to 73. 18 and 9 becomes 27. And 73 plus 27 is 100, which is what I wanted. That's awesome. So the numbers work out then. You just have to take into account the fact that you double counted a certain number of people. So let's see. How many of the students surveyed are fans of both the Buffalo Bills and the New York Jets? That's going to be 18. And the probability, if I wanted to add that on to question number 27, of Jets and Bills would be 18, because that's how many fans are both, out of 100 total. But that wasn't really what they asked, that was the answer. And you might want to specify 18 people, 18 students. Now, I just want to clarify one thing about mutual exclusivity. These two are not mutually exclusive. Okay? These two are not mutually exclusive. The concept of mutual exclusivity is that things are mutually exclusive if they have no overlap. If the middle of the Venn diagram is empty. So for instance, if I wanted to give you a mutually exclusive example, it might look something like this. If I flipped a bunch of coins, and that gave me a Venn diagram. I flipped a bunch of coins, and let's say that this is heads, and this is tails. Let's say I got 56 heads. Clean that up. And I got 44 tails. Are there any results that are both heads and tails? Is there any way that I could have one coin land on both heads and tails? It's actually impossible. So the inside has to be 0. These are mutually exclusive. And that's the concept. Cool. So I will see you in class.